Hello and welcome to Maths with El Profe Lo, doing some work on elementary number theory and in particular linear congruences in one variable. Okay, we've talked about these linear congruences of the form AX is equivalent to B mod M and how they have solutions only if the greatest common divisor of A and M divides B. Right? If that greatest common divisor does not divide B, no solutions. If it does divide B, we have exactly D incongruent solutions. Okay, and something that can help us solve these is our cancellation theorem, right? Which says that CA equivalent to CB mod M with CM greatest common divisor D, then A is equivalent to B mod M over D. And of course, these incongruent solutions, when they exist, take this form. All right, so we're going to practice with a proof to prove that if AX is equivalent to AB mod M and the greatest common divisor of A and M is D, then X is going to be equivalent to B mod M over D. All right, so I do want to point out that the form of the equation is very similar to the form of our equation in the theorem, or our congruence, excuse me. So the form of the congruence is very similar to the form of the congruence here. But in addition, it is also taking the form of the cancellation theorem, where instead of saying CA and CB, we're saying AX and AB. All right, and so then that's changing X equivalent to B rather than A equivalent to B. Okay, so let's come through here. All right, so let's do this. So we're going to let A, B, M, and I'm going to add a couple of letters here, R, S, and T. We're going to let all of these be integers, right? And in particular, M is going to need to be positive. So M will be greater than 0. Okay. Now, if I have AX is congruent to AB mod M, then the implication is that AX can be written as KM plus AB, right? It can be written as some multiple of M plus AB. And it looks like I forgot to include K in here. So we're going to say that K is going to be some integer as well. Okay. Now, if D is equal to the greatest common divisor of A and M, then the implication is that D divides A and D divides M. And it also implies that there exists A being equal to R times D and M being equal to S times D, where R and S are relatively prime, right? That it'll be possible to write A as a multiple of my greatest common denominator, and M as a greatest common divisor, and possible to write M as a multiple of my greatest common divisor, where R and S are relatively prime. Now, the reason R and S have to be relatively prime is because D is the greatest common divisor. So there's nothing in common between R and S in terms of their prime factorizations. Okay, so taking this and substituting into our equation, right? Therefore, we can say, right, so I'm going to replace A with RD, so I can say that RDX is going to be equal to RDB, right? So RDX is going to be equal to RDB mod SD, right? Which is going to indicate that RDX can be written as KSD plus RDB. Okay. Now, moving things around in this equation, I can say that RDX minus RDB is equal to KSD. And since D is non-zero, as it is the greatest common divisor, I can say that Rx minus Rb is equal to Ks. So therefore, factoring out an R times x minus b is equal to K times S, which implies that S divides R times x minus b. Right? However, since S and R are relatively prime, therefore, only S divides x minus b. And if that is true, if S divides x minus b, the implication there is that x minus b can be written as a multiple of S. So S times T. Okay? Which we could say is really just T times M over D. Alright? So therefore, X has to be equivalent to B mod M over D, which is what we were trying to prove. Okay? So this cancellation theorem is true. All right? How can we use the cancellation theorem? Well, let's solve this particular congruence. And notice that for this congruence, the remainder is greater than this value of m, which is fine, right? And sometimes you create this situation in order to be able to solve your congruences, right? And so if we come through here and we say, okay, so 9x is equivalent to 144 mod 99. Well, what do we know? 9 and 99 have a greatest common divisor of 9, and 9 divides 144, right? Because the sum of the digits of 144 is 9, 4 plus 4 plus 1, so 9 divides 144. Okay, so therefore, using our cancellation theorem, right? Using our cancellation theorem, we can say that x, right, will be equivalent to 11, let's see here, not 11, 16, right? 16 mod 11, right? And the reason it'll be 16 mod 11 is because 144 divided by 9 is 16, and 99 divided by 9 is 11, and of course 9 divided by 9 is 1. So 16 is going to be equivalent to 16 mod 11, all right? So therefore, we could say that x is going to be equivalent to 5 mod 11 to make things a little bit easier for us. And that then tells us that x naught, our first solution, right, can be 5. And then our next solution will be 11 more than 5. That'll be 16. The solution after that will be 11 more than 16, which would be 27. And the third solution would be 38. And the fourth solution would be 49. And actually this would be the fifth solution, right? So x of 0, x of 1, x of 2, x of 3, x of 4. This would be the fifth solution, right? Then x sub 5 would be 60. X sub 6 would be 71. X sub 7 would be 83, and x sub 8 would be, oops, no, this would be 82, and x sub 8 would be 93, right? So these would be the 9 incongruent solutions, right? 5, 16, 27, 38, 49, 60, 71, 82, and 93. These would be the 5 incongruent solutions that could solve this particular equation, right? And of course, we could always double check. We could always double check this and say, hey, you know, will it really work with 93? Well, let's see. 9 times 93 is 837, right? If I subtract, let's say 99 times, let's do minus 99 times 8. All right, that's going to give me 45. And if I add 99 to that, hey, look, that's where I have the 144. So it works there. If I had 9 times, let's do 27. And that's 243. Subtract 99 once. And look at there. I have 144. All right. If I said 9 times 5, that's only 45. But we've already said if I add, right, if I add 99 to that, that's going to get me that 144 as well. So then clearly these are our solutions. And of course, using and being able to use this cancellation theorem is very, very helpful in solving. Right? And these ideas of these cancellation theorems do come up in other areas of number theory. Thank you for taking time with Maths with el Profe Lo. If you have questions, please do reach out.